This talk is to introduce our paper, Logical Fallacy Detection at EMNLP 2022 Findings. This is a joint work among Zhijing, myself, Abhinav Lalwani, Tejas Vaidhya, Xiaoyu Shen, Yiwen Zhiheng, Mrinmaya Sachan, Rada Mihalcea, and Bernhard Schoelkopf. Our motivation comes from the recognition that there are two orthogonal skills, one about the knowledge and the other about logical reasoning. If we see the sentence, sometimes flu vaccines don't work, it's a correct fact. However, people could make a wrong reasoning that all vaccines are useless, which is a logical fallacy of faulty generalization. What we see here is that to reach the right conclusion, there could be two orthogonal skills. One is the logical thinking, and the other is factual knowledge. And in this paper, why do we focus on the logical reasoning part? There are several motivations that we consider. Mainly, it's about the facts are not enough. First, if we think about the case of misinformation, the topics could be moving targets, and also fact-checking everything could be quite expensive. Also, there can be things that are beyond all acceptable facts, but we still want to grasp a knowledge of. One visualization of it is to look at the cost curve. If we think about accumulative cost for fighting misinformation when the topics keep varying over the years, then we will see that the cost for collecting and verifying facts keep increasing. Whereas to check the logic, it's close to constant because the logical forms are the same across different topics. The other visualization of the usefulness of logical thinking is that among the different topics, there could be big, well-funded topics that are both okay to run logical check and the knowledge check. But there could also be other topics that maybe the checking the logic is a more reasonable way. These topics include less funded ones, new urgent ones that people are have not yet formed a database of, such as the first months of COVID. And then it could also include cases that are beyond the best empirical science we can achieve. So scientists can only logically reason about what could be the actual thing behind. And then after arguing about the motivation by just reasoning, we can also see some real world cases about how no matter how diverse the topics are, we can see that they keep repeating a common set of logical fallacies. If we look online across the news and also political statements, we can see many examples such as confusing correlation as causation, or arguing that if you cannot prove I did not suffer from voter fraud, then I did. So that's a clear case of false dilemma. And then there could also be other cases of personal attack and faulty generalization. So the contribution of our paper is that is in 4 ways. First, we propose a new task, logical fallacy classification. Second, we construct a data set. The main part of the data set is 2,400 general logical fallacies. And then in addition, we also provide a challenge set of climate change claims. Then we look into how existing large language models perform on this. So we run 12 different existing large language models and benchmark their performance on this data set. And lastly, we propose our new model of a structure-aware model, which can improve 5.46% over the best baseline. So now let's look into the data set. As we mentioned, we have 2 parts, the general logical fallacies and logic climate. the detailed statistics of the main data set, the general logical fallacies, are shown here. On the left, it's the number of samples, sentences, and tokens vocabulary, these statistics. On the right, we show the distribution over different logical fallacies in this data. Some more examples of the top 5 common classes are shown here. So we have faulty generalization, ad hominem, ad populum, false causality, and circular claim. With this data set, we aim at 2 types of impact. First, technical impact. This data could be used to check the trustworthiness of existing models, advance argument mining, enhance reasoning ability. And also in terms of the social impact, it can help fight misinformation with potentially low cost, inspect political devices of persuasion, and promote critical thinking in education. One way to think about the impact could be as follows. In our data set, which contains general logical fallacies in daily language, we could have examples such as, she is the best because she is better than anyone else, which is a circular reasoning. And then we can imagine that if we can master this task, then the model could be applied to various other topics like political claims, climate claims, and so on. And then we could see that maybe in the future political campaign, if there's a statement claiming someone is the best candidate for president because they're better than any other candidate, we know that logically it's fallacious. It's not really supporting the argument by any concrete evidence. Or a climate change claim that global warming doesn't exist because the Earth is not getting warmer. It's basically repeating the argument again. And then now let's look into how the models can perform on this data set. We first look into how existing large language models deal with it. So compared to the random baseline, we can see that almost all the zero-shot classifiers barely outperform the random baseline. And then if we fine-tune pre-trained models on the logic data set, we can see that the best performance is 53% F1, which is still not yet satisfactory, thinking about how prevalent the application cases are for this use case. Then we look into the model that we propose. So the inspiration we start from is that many of the cases, it's the form of the argumentation that matters a lot. We can see several cases here. The circular claim case is mainly has a structure of a claim, stating a claim because, and then paraphrase the claim again. And then for false causality, it's basically describing 2 events happen together, therefore one causes another. And then for the deductive fallacy, some of the cases could be if A, then B, and then that does not mean if B, then A. So what we do here is that we try to augment the natural language inference NLI framework with structure awareness. So we look into both the premise and the hypothesis. In the premise, we have we put the input like claim into it. So in this case, Jack is a good athlete. He comes from Canada. Therefore, all Canadians are good athletes. And then what we do is that we want to shift the attention from the actual content to the logical form. So we do coreference resolution, cosine similarity calculation over the spans, and then detect the different spans that are paraphrases of each other. Then we replace the paraphrase spans with the same mask. In this case, we only know what is being repeated, but not like the exact content of the exact content of each span. So we end up with a mask form in the premise. And then in terms of the hypothesis, the general way to use NLI framework for classification is to say that to compose a hypothesis in the form of this is an example of a certain class. And then what we think is that just the surface form of the name of the fallacy is not enough. It's probably much better to write out the exact fallacious logical form. So what we have here is to write out the template for faulty generalization, also using the notation of masks. Then we plug both of them into the pre-trained NLI model and fine-tune the entire system together. Now let's look into the model performance. We can see that, so what we do is that we take the best performing large language model from all the ones that we fine-tuned. In this case, Electra is the best performing one. And then we add the structure awareness on top of it and show that this increases the performance by 5%. And then in addition, we also check the transfer performance of our model. So the setting we have is to train on logic, the general fallacies data set, and then test it on climate change claims. So what we have here is on the left is an example of false causality in the general fallacies and false causality in climate change. And then we can see that with structure awareness, our model performs better than the baseline as well. And then to conclude our contribution in this work, we propose a new task and supported with a data set we collected, benchmark existing large language models, and propose a possible better way to highlight the structure awareness of large language models. And the links to our paper, data, and code are also shown here. Thank you for your attention.